Welcome to our next topic. That is, to, we are going to discuss applications of radioactivity. And one of the important application of radioactivity is radioactive traces or in tracing techniques. What do you mean by radioactive or tracer technique or radioactive traces? In radioactive tracer technique, we are using a radioactive isotope or its compound introduced at a one point of a system, and its movement is then traced by measuring the radioactivity in different parts of the system. So by using that one, we get a lot of applications are there. Such isotopes or their compound are known as radioactive traces. Now, so trace the some reaction or not to analyze the cracks in a metal pipe and that kind of applications we are using these radioactive traces. A number of radioactive isotopes are used in tracing various processes in surgery, medicine, biology, agricultural, and industrial application. Some examples are there in medicine. There is, for example, in surgery, not to find out if blood is circulating to a wound or not. So for that one, we are injecting a radioactive isotope into the body, and after suitable time, the blood from the wound is examined from based on its injected radioactive compounds or radioactivity of based on the radioactivity of the compound, and so that is one of the example application of radioactive traces in medicine. Or another example is P34, phosphorus 34 is used to check the bone fracture. Another example for radioactive tracer, it is phosphorus 34. In agricultural field, we are using this one example is calcium phosphate containing radioactive phosphorus is generally to trace the take of phosphorus by plant. Not to study the phosphorus by plant, we are injecting calcium phosphate that contain radioactive phosphorus, then analyzing its radioactive properties, we are able to trace the uptake of phosphorus by the plants. Then in industry, there is metal castings are tested for cracks by putting them in a radioactive salt bath. The casting are inspected afterwards for the radioactive to find out if penetration of the salt into the crack has takes place or not. If absence of salt indicate the absence of crack. In that way, we can analyze the crack in a long pipe by using this radioactive traces. These are the one of the application of this radioactivity, radioactive traces, and examples of radioactive traces. Next application is dating technique or rock dating in order to find the age of earth or age of the minerals or age of the materials by knowing the overall disintegration of a radioactive isotopes, and we can be able to calculate the age of a mineral, and that technique is known as dating techniques or rock dating. That is based on the time for which disintegration has been going on. This gave approximate idea of age of the earth, and this technique is known as dating technique. According to radioactive series, the ultimate product of uranium disintegration, that is uranium series is in the air radioactivity. So uranium disintegrate to give a stable lead with the mass number 206. By using analytical techniques or microscopic technique, it is possible to determine the ratio of amount of uranium to that of lead in the given rock. Knowing the overall rate of disintegration of the uranium to lead, it is possible to calculate the age of the rock. And that is one of the important applications to find the age of a material, and that is known as dating technique or radio dating techniques. Then next is carbon dating to determine the age of widely using this on carbon dating. What is the carbon dating? William F. Lippey won the Nobel Prize for developing highly one of the important techniques of carbon dating to determine the length of time for which a body had remained alive or age of a material or minerals by using the carbon. That is, radiocarbon dating is a method that provides objective age estimates of for carbon-based material that originate from living organisms. How we can determine the age by using this carbon dating? We are going to see how we can measure or how you can find the age using this carbon dating techniques. As we know, carbon has three important isotopes, that is C12, C13, C14 with the mass numbers 12, 13, and 14 respectively. And as we know, this C12 is most common with the abundance of 19.89%, but C14 is formed only in traces in the atmosphere by cosmic neutron bombardment of nitrogen, and it is radioactive in nature. That is CN14.7 is nitrogen when bombarded with neutron, it gives C14.6 plus phosphorus, and this it undergo. If this one is radioactive in nature, so it undergo beta decay. That is C14 plus C14.6 gives N14.7 plus beta particles, and this C14 has half-life period of 5,568 years. Based on this one, we can find, based on this principle, based on this one, can able to find the um, age of a material. How we can find the, or what is the basic principle of this radiocarbon dating? That is, carbon 14 is an isotope of the element of carbon that is unstable and it is weakly radioactive. The stable isotopes of carbon are 12 and carbon 13. Carbon 14 is continuously being formed in the atmosphere by the effect of cosmic neutrons, cosmic ray neutrons on nitrogen 14. That's we already seen in the above equation. And this carbon dioxide, along with the most common C12O2 by plants in 10 animals. That is, this carbon 14 is readily oxidized in air to form carbon dioxide and enter the global carbon cycle. And this carbon dioxide, and along with the most this C12O2 that is absorbed by plants and in animal, and plants and animals simulate carbon 14 from carbon dioxide throughout their lifetime. When they die, that is in the lifetime, when they die, they stop exchanging carbon into the biosphere, and their carbon 14 content start to decrease at a rate determined by law of radioactive decay. That is, in the plants or animals, there is carbon containing C14 and C12 is there, but this C14 that can present in the plants, that is radioactive in nature. That after the death they start disintegrating. Then what happened? The 14 the C14 which is in plants and animal body has accumulated during its lifetime now begins to decay by emitting beta particles. According to the equation number B, with a half-life period of 5,568 years. The decay rate, that is the number of beta disintegration, that is N0, just at the time of the death of the plant is around 16.1 counts per minute per gram of carbon. By carefully measuring the decay rate of the dead sample at any period, it is possible to determine the age of the sample. So we take, suppose the decay rate of sample of wood is found to be N disintegrations per minute per gram after T years, then N is equal to N0 e raised to minus lambda T, where N0, what is N0? The decay rate of number of disintegrations just at the time of death, that is denoted by N0, and N is the disintegration per minute at time T, and lambda is known as decay constant. Disintegration constant, N0 disintegration per gram just die. Take log of this equation. Ln N is equal to ln N0 minus lambda T. Our aim is to find the T, is the year time. So, not to find lambda, here we T half is there, so observation between lambda and T half, that is lambda is equal to 0.693 by T half. Knowing the half-life period of C30, substituting this value of the C14 is 568 years, then value of lambda, hence T, the life of or age of the specimen can be calculated. You know, in the N0 lambda, we can able to calculate T. and that is the determination of age by a dating technique, or and it is called the radiocarbon dating. The important application of the radioactivity. Next, we're going to discuss some numericals based on this one, radiocarbon dating. The question is like this: a freshly cut piece of wood gives 16,100 counts of beta ray emission per minute per kilogram, and an old wooden wall gives 13,200 counts per minute per kilogram. Calculate the age of the wooden wall. The half-life period of C14 is 5,568. So here n is there, n0 is there, half-life is there. So we can easily find out the t. So we can find the t as with the basic equation is n is equal to n0 e raised to minus lambda t, ln n is equal to ln n0 minus lambda t. In this present case, what is n? Number of disintegration per minute per kilogram. So that is equal to 30,200. That is counts per kilo volt at time t. That is 30,200. Freshly cut piece, that is at the time of death, that is n0. Just died is 16,100. So both the units are same. So we get t half is equal to 5,568. From the t half-life period, we can calculate disintegration constant lambda, that is equal to 0.693 by t half, that is equal to 0.693 by 5,568. Substituting these values in equation, we get ln n is equal to ln n0 minus lambda t. So rearranging this equation, ln n by n0. So this one is the ratio. So disintegration per minute per kilogram and disintegration per, that cancels. So minus 0.693 by 5568 into t. So ln 30,200 by 1600 is equal to minus 0.693 by 5,568 into t. Rearranging, we get our aim is to find the year time taken to degradation, or the age of the sample, that is t is equal to minus 5.68 divided by 0.693 into 0.1986, that is equal to 1,576.3 years. That is the life of this particular wood. Hope you understood how to find the age of a particular material by using this radiocarbon dating. Then come to another example. The question is like, a living plant acquires definite fraction of C14 6 nuclei in its carbon content. If a freshly cut piece of wood gives 16.1 counts per minute per gram, and an old wooden hole gives a 19.6, that is freshly, this one is n0, this one is n, 9.6 counts per minute per gram. Calculate the age of the wooden bowl. Half-life period is there, is 14, 6 is 5,770 years. Then how you can calculate? That is n0 is 16.1, n is 9.6, or n0 is there, n is there, half-life period is there. So we can calculate n is equal to n0 e raised to minus lambda t, ln n is equal to ln n0 minus lambda t. Our aim is to find the value of t. So lambda is equal to 0.693 by t half is equal to 0.693 by 5,770. Substituting these values, ln n 9.6 is equal to ln n0 16.1 minus 0.693 by 5,770 into t. Rearranging, ln 9.6 by 16.1 is equal to 0.693 by 5,770 into t. So solving, t is equal to 4,305.07 years. In that way, we can calculate year of a particular age of a specimen by using this technique. Hope you understood. Thank you.